This riot took place in 1972 in a prison. Unrest in prisons is one of many serious social problems. But what's that got to do with mathematics? The connection is a new branch of mathematics which is being used to analyze prison riots, and the use of this new mathematics has become quite controversial. It's called catastrophe theory. To see how mathematicians became involved in this social controversy, you need some idea of what catastrophe theory is about. We went to Warwick University to see one of the main proponents of the theory, Professor Christopher Zeman.
Catastrophe theory is a method of modeling discontinuous phenomena. It depends upon some deep theorems in mathematics, but before I explain one of the theorems, I'd rather like to show you a small toy which illustrates discontinuity. Made of a disc of cardboard which can rotate freely on a drawing pin at the center, and two elastic bands which are attached at one point on the perimeter of the disc, and one of the other ends of the elastic band is held fixed, and where I hold the other end of the other elastic band is called the control point. Now, I can move this control up and down and sideways, and so the control space is two-dimensional, this plane. Meanwhile, the behavior of the machine is the position of this disc, and I can measure that by the angle that this line makes with the vertical. I call that x. And as I move the control, then the behavior responds smoothly most of the time. If I move it in certain ways, then the behavior will respond with a sudden jump. And if I move it the other way, it'll jump the other way. Now, this jump is surprising because it's against our intuition, our physical intuition. When we normally apply continuous forces, we expect continuous effects. But when discontinuous effects happens, and it happens to be bad and large, we often call it a catastrophe, and that explains the name of the subject. Now, what I want to do is to explain the behavior of this little machine in terms of a geometrical picture, a cause-effect graph, with the cause horizontal and the effect vertical. Now, the cause is the control space, so in fact it's a two-dimensional plane. So I really should draw this as a two-dimensional plane. And you have to imagine this coming out of the paper. So this is the control space. Meanwhile, the effect, x, is the position of the disc, which is measured by the angle, and we'll assume for simplicity that this angle runs from plus 90 degrees to minus 90 degrees. Here's naught. Now, supposing I fix the control point here, then the disc will take up the unique position of stable equilibrium. So, above this point here, I will put the corresponding, mark the corresponding point of stable equilibrium with a blob. That's control point number 1. So now let me take another control point number 2. Here, this is more in the center. Now, when the control point is in center here, there are two stable equilibria, one there, one over the other side. And they're separated by an unstable equilibrium in the middle, which, if I perturb slightly, will then flick into one or the other of the two stable equilibria. So, above this point 2, I now have to put two blobs representing two stable equilibria, one here and one here, separated by a cross which represents an unstable equilibrium in between.
But why does the machine jump? This graph represents the energy stored in the elastic band for a particular control point. The minimum value of energy gives the stable equilibrium position. As the control point moves, the energy changes. A second minimum appears to the left. But the machine stays in the first minimum until here. The right-hand minimum disappears, and the machine jumps to its other position. If we move the control point back, the machine stays in the left-hand minimum until it disappears.
We must now turn this into mathematics. It is possible to choose coordinates A and B in the control space and suitably scale the coordinate x here, such that the energy function in the elastic bands, V, is given by this formula x to the 4th over 4 minus ax minus bx squared over 2. Now, if we fix A and B, here is a typical picture of the energy function, and what we want to find is the minima and the maxima of the energy function where the slope is 0, and so that is given by partial derivative dv by dx equals 0. And so that is the formula differentiating the line above, x cubed minus a minus bx equals 0. And that's the formula in three-dimensional space for this cubic surface.
But where does the surface come from? Start with the equation for minimum energy. When b equals 0, it's just the cubic, x cubed equals a. As before, we've shown x vertical, and a, one of the control variables, is horizontal. When b equals 1, the curve looks like this. It overlaps itself. And when b equals minus 1, it becomes quite flat. As b changes continuously from minus 1 to plus 1, the curve changes like this. But now, imagine a third axis for b. If you draw in the curves for different values of b, you get a surface.
Here's a three-dimensional model of the surface, which enables you to get a geometrical feel for it. It's important to remember that the fact that this is solid and this is air is not significant. You should try and think of the surface as floating freely in space. The upper and lower sheets are representing stable equilibria, and this undersheet here represents unstable equilibria. At the back of the surface, we have a nice continuous behavior if we've moved the control to and fro. But if we have the splitting factor this way, then when we move the control to and fro here, the behavior comes along to this point and then does the catastrophic jump, and backwards does the catastrophic jump backwards again.
You can see what this means in the control space by looking at the surface from above. The region where the surface folds back on itself is shaded in more heavily. Notice it has a sharp point. Phenomena like this were analyzed by the French mathematician René Thom.
When we project the fold curves down onto the control space, they create a sharp point, which is called a cusp point. Upstairs it's quite smooth, but downstairs we get a cusp point, and this is why we call the whole surface the cusp catastrophe surface. Now, we can take this cusp, now transfer it back and put it on the machine, on the control space of the machine. In actual fact, there are 4 cusps, each of them behaving similarly, and forming a concave diamond, which separates the control points outside, where there is only one stable equilibria, from the control points inside, where there are 2 stable equilibria. And this picture is just a picture of what happens in the neighborhood of this bottom cusp point. We can now explain the behavior of the machine in the neighborhood of this point by the geometry of this surface. I start on the lower surface and I gradually move to the right, and when I reach the right-hand side of the cusp, it jumps onto the upper surface, and when I move back, with luck, when I reach the left-hand side of the cusp, it should jump back. It did.
Of course, not all the applications of catastrophe theory are controversial. One application is in physics, to the study of light rays. This is the moon's reflection sparkling on the sea. Each spot of light shows where the water surface is reflecting the light to your eye. But look closer. The images come and go in pairs. Why does this happen? If these are the rays from the moon, then only some of them will reach your eye, those which hit the water surface where it has the right slope. But the surface won't stay still. If it changes like this, then suddenly both rays disappear with a twinkle. Now you don't see reflections from that part of the surface. This happens because the length of a light ray must be a minimum or a maximum. If you plot the positions of these minima or maxima, they lie on a curve, like this. As time passes, a pair of dots appears together. Then they disappear with a twinkle. So this is a situation where catastrophe theory may be applied. The continuous movement of the water surface produces a sudden discontinuous effect. And Thom's theorem predicts that, under normal circumstances, spots of light will only appear in pairs. Some of the modern research in this subject is being carried out at Bristol University by Michael Berry.
What happens at a twinkle is focusing. The water surface doesn't just have the right slope to reflect light into your eye, but also the right curvature to focus it there. Now, you probably think that a focus is a point in space like this. But such a thing is really very special. It's the result of lens designers' skill. Mathematically, it's unstable, and the focus from a less particular refracting object, such as these water waves that we've been speaking about, is a complicated surface in space called a caustic surface. The word caustic comes from the Greek word for burning, referring to the intense heat in focused sunlight. Thom's theorem is helpful because it describes typical focal patterns, that is, the forms of caustics which arise from reflecting and refracting objects likely to be found in nature. In 2 dimensions, the fold catastrophes are caustic lines, and Thom's theorem says these can meet at cusp points. Actually, this is far from obvious because it rules out as being unstable such things as caustics with finite angled corners, or fold lines with ends, or isolated focal points like the lens I showed you. It's quite easy to make cusps. The secret is to use not glass lenses, but water droplet lenses, which are made irregular by spraying them from a considerable height onto a piece of dirty glass, and then shining a spread-out laser beam through these irregular lenses onto a screen. It's quite obvious from the images that cusp catastrophes do indeed dominate the focal patterns. In fact, the deepest application of Thom's theorem in optics is not its classification of caustic forms, but the way in which it can be used to describe the finest details of the vivid interference patterns close to caustics. Here's interference near a cusp in the form of a computer simulation based on Thom's theorem. And here is the same pattern in practice, produced by focusing a laser beam through irregular bathroom glass onto a screen. It's evident that theory and observation are in very close agreement. These are some of the ways in which research at Bristol is proving catastrophe theory to be very useful in optics.
But it's when catastrophe theory is applied in areas of social concern that it becomes most controversial. For example, when it's used to analyze prison riots. One of the prison psychologists involved in this application is Peter Shapland.
In Gartree Prison in 1972, there was a series of disturbances in the prison which ended up with a major disturbance towards the end of the year in November. A short time after that, it seemed to us a sensible thing to see if, with the benefit of hindsight, we might have been able to predict the events which occurred. In order to do this, we went to the prison and assembled all the relevant items of hard information that we could find. These are the kinds of things that are routinely collected for administrative purposes. During this time, I'd been discussing with Christopher Zeman catastrophe theory, and it seemed to me that the riot situation in particular was likely to be a very suitable application for catastrophe theory, and of course extremely relevant for the prison department.
Yes, it was clear that the riot was a jump in the disorder level of the prison. Now, if we were going to apply this type of mathematics, we should have to look for parameters which would act as a control space. So the first thing we did was to collect these 25 indices and work out a correlation matrix, do factor analysis, that is, choose the eigenvalues of this matrix, and this procedure gave us two factors which seemed reasonable to call tension and alienation. We then plotted the data for the 52 weeks as a time path in the tension alienation plane. And somewhat to our surprise, it seemed to wiggle down inside a cusp. Now, of course, we would like to have plotted the three-dimensional surface, but we didn't have enough data for the disorder level to be able to do this. So we couldn't actually deduce the cusp from the surface. We had to guess a cusp shape. Now, in fact, we put in two cusps, one before the first mass demonstration and the other after the first mass demonstration. You can represent this as a movement of a cusp in the control plane due to the fact that since the expectation level of disturbance was higher, new regulations were introduced which permitted a higher level, a higher tolerance of tension before outbreaks took place. However, I should emphasize that this is rough data and retrospective data, and before we can say whether the model is proved or disproved, we really need to investigate many different prisons over several years and try and use the model as a predictive tool.
Yes, I think that's very true. I think indeed we were surprised to find the kind of time path that emerged. On the basis of that evidence, it seemed to us that this was really worth pursuing, and so we arranged for the monitoring to be instituted at Gartree as a matter of routine, and this has now been going on for, it must be just over 2 years. It's worth emphasizing, I think, that it is very much in a developmental stage, and of course from the point of view of the prison department of the Home Office, catastrophe theory in this sense has no sort of formal status or recognition, but we are in a development stage and are likely to be so for some time to come.
This use of catastrophe theory has been attacked very strongly, as in this article. Here's Jonathan Rosenhead.
Well, there are two different sorts of objections. One of them is a technical sort of objection, The other one is, I think, more important, which is to do with the theory which underlies the approach. Let's take the technical ones first. For some fairly simple things like the fact that when they actually plotted their observations of disorder in a prison, they found that the results that they were getting did not, in fact, fit within the predicted cusp region. And they had to rescue their data by presuming that the cusp moved somehow in the middle of the period under study. And if you look at the data points, without the cusp that they've drawn on them, there are many other shapes which you could see as much more likely that they fall within. What's actually happened is they've made certain assumptions which make a catastrophe theory inevitable. So they choose their assumptions conveniently to produce a catastrophe. But those assumptions, in fact, are not especially plausible and certainly not unique. One could make many other sorts of assumptions about what were the underlying factors in a prison riot.
I appreciate the nature of the criticism. I think the difficulty is actually to come to terms with measurement in this very complex kind of organisation. Any kind of measurement really is extremely difficult. We used, or tried to use, all the available information that there was in the prison at the time, and as we said already, we were really quite surprised at the results it produced. Certainly it encouraged us sufficiently to develop the model further. I think I'd take a pragmatic approach that really the proof of the pudding is in the eating, and it depends very much on the use to which the system is put in prisons, the value that is placed upon it by management, and I think merely because something is simple, that is no single reason for dismissing it.
But the main thrust of Rosenhead's argument is about the way mathematics is being used to regulate and control people's lives.
I don't think mathematics is any worse than any other mechanism that can be used for control, but it does add to the control repertoire certain rather specific and novel features. And I think one of the main ones of these is that it distances people from the consequences of the actions that they may take. If they're basing it on the sort of abstraction of a mathematical theory, then they somehow feel not responsible for what may result. What can happen, I believe, is that people, particularly those who are not very well versed in these techniques, can become so impressed with the jargon, and I believe even the mathematicians themselves can become so impressed with the jargon that they fail to notice that what they're actually doing is they're giving an answer, which may be right or may be wrong, but it's the wrong question that they're trying to answer.
I think one could equally well put it back in terms of should one use mathematics to help people in this situation. So far as I'm aware, of course, it's not possible to use this kind of information to control prisoners. All this information is readily available in any prison, and all that we have done is really try to assemble it, to put it together in a different framework, and to see whether it can be used to be, as we would consider, helpful in the situation.